Okay, next we are going to solve this example problem. It is on page 329. Example 35. A motor spins a wheel with a constant angular speed of 200 RPM. The motor is then turned off, and friction in the motor causes the wheel to stop spinning after a quarter of an hour. We will determine the constant acceleration in revolution per minute square as the wheel is brought to rest, how many revolutions the wheel makes before stopping, and the tangential acceleration of a particle located 60 centimeters from the axis of rotation when the angular velocity is 125 rpm, and the radial acceleration of the particle described in part C. So there are several things, and you can see that the units are all over the place. So we gotta focus on the units as well when we are solving problems. Okay, so but in general, this topic is very similar to chapter 2. Okay, so it's like I don't want you to see this as very complicated problem. We do know how to deal with these type of problems, and step-by-step process is really the way to go. So we know what is given, what is to find. Figure, again, we have this counterclockwise motion shown with the arrow. This is how we're going to take this counterclockwise. And r is shown, theta is shown with the horizontal. First of all, we are assuming constant acceleration, right? So it's constant angular acceleration. And this is a rigid body rotation as well, it's not a particle. So we will use the rotational motion equations to relate things. And if we estimate angular acceleration of the disk in revolutions per minute square, it's going to be, first of all, negative because it had the speed and slowing down to, and we are bringing it to rest, right? So it has to be negative. Assuming omega is positive, and we already assumed that in the figure. And we can also approximate the number of rotations. So we have about 100 revolutions per minute. Again, if you do it in order of magnitude. And for 10 minutes, you get about 1,000 revolutions, right? So it's like you can, since quarter of an hour is like 15 minutes, so if you do it in order of magnitude, it's not too hard to figure it out. It's like about 1,000 revolutions. It gives you an order of magnitude estimation. And part C is tangential acceleration. This should also be negative, right? And again, because it's slowing down, at least like mentioned the something that you can easily see. And the radial acceleration for part C is comparable to gravitational acceleration, right? So in terms, because it's the radial acceleration, that's the linear case, and so we are going to figure out the numbers. The finding numbers and estimating numbers are hard a little bit because we have like big numbers, small numbers, and the units are all over the place. But again, try to understand what is it related to, or is it positive, negative? I'm dealing with vectors. Kind of review those things before you solve the problem so that you prevent making mistakes later on. Okay, so first part, angular acceleration of the disk in revolution per minute. So we want to get that angular acceleration. So we have two equations, right? This is our step 1, writing position and velocity equations, but these are now in angular form. And step 2 is writing what we know at the start and at the end. At the start, we know that omega 0 is 200 RPM, and we will define theta 0 to 0. Okay, so we're going to cross that out. And at the end, we know the time is quarter of an hour. We said that initial time is 0. And final angular velocity is 0. So that this is going to go to 0. Okay, so this is our step 2. And now we're going to do step 3, which is put things together, right? So theta becomes, theta 0 goes to 0. So omega 0 times time plus 1/2 alpha t squared. So just like we're writing the simplified version of the equations. Since omega is 0 for the angular velocity, we have 0 equals to omega 0 plus alpha times t. That's the second equation. And now if we continue with the velocity equation, we have 200 revolutions per minute, and the time is 1 hour. But if you're going to use revolutions per minute, then you need to convert the hours to minutes. Otherwise, you cannot add these two, right? They will be in two different dimension units. And after using this conversion factor, you're going to get rid of the hours, and in 1 hour we have 60 minutes. So then you're getting also minutes here. That will make it consistent. And solving for this, put this on the other side, becomes negative. First of all, divide by the rest of it, so leave alpha alone, and you divide by 15 minutes then, and that gives you negative 13.3 revolutions per minute square. Okay, that's the units. Again, this is kind of radians per second square, but in different unit. It's not an SI unit. And the second part, because be careful with this too. It is asking you to find the answer in revolutions per minute square, so you have to convert it to that. If you solve the part A in terms of SI units and then convert it, it was more work. So that's why we just kept everything in revolutions and minutes, so that we can get that answer. Okay. Just be careful with the consistency and what they're asking for. If it is asking for radians per second square, then you need to convert it. If it is not specifically saying something else, then you need to keep it in SI units. Okay, so number of rotations made. So this is, we did part A. Now we're in part B. Number of rotations made during the stopping process. So now we are focusing on theta. And again, we have this equation here. So we're just going to use that. We have more stuff now. We know what alpha is. So we're just going to plug this in, right? And we had the simplified version. We have some conversions again. Omega 0 was revolutions per minute, and t was in hours. So you need to use this conversion factor to convert it to minutes. And this is our alpha here, 1/2 alpha, and this is our t square. Once again, you need to convert it to minutes before doing anything else. So we did convert the time here and time square here. And if you check your units, minute squares will go away in here, and then minutes will go over there. So these two and these two. Then you're going to get revolution, as you should. So please follow the units, and you know that it's required every time when you're solving numerical problems. But it's more crucial because we have so much, we may have so much conversions in the problem. Okay, this is 1500 revolution, and that's our theta. So let's also box this. And part C. So we got part B, tangential acceleration of a particle 60 centimeters from the center when omega is 125 RPM. I think I'm gonna continue that in the next part because I don't want to make it like a long video for this part.